This is Introduction to Databases, and it is the final lesson that I will personally be presenting for our Systems Librarianship 101 series. And then we are going to have some presenters from the Orbis Cascade Alliance for the following lessons. And this lesson is going to be a little shorter than the previous presentations, which I think a lot of people will appreciate because there was a lot of information to stuff in those previous topics. And though there is a lot of information that I could stuff into a presentation about databases, there are other sources that do it better. So I am going to restrict this presentation to simply an overview of the types of databases that you might work with as a systems librarian and an explanation about indexes. And then you can go and learn more about how to build these databases and query these databases using various languages on your own time. So this lesson has a very short list of topics, and you can read the full text here at this URL. So first we'll go into database types, very broad overview, high level. First, there are hierarchical databases. This is the oldest and most inflexible type of database, originally used in the 1950s and 60s when computers were shiny and brand new. And this is a very simple scheme of trees of parents and children, like an ancestral family tree. And I have an example on the next page. Or like the file systems in Windows, Linux, and older Apple devices, where a single object can exist within a parent and only one parent. So this accommodates one-to-many relationships only. And here's my illustration of the Windows file system that most of us are familiar with. You would have a drive. So this is a logical partition, like the C drive. And then within that drive, you have these subdirectories, program files, users, windows, many more as well, but this is what fit into the graphic. And then within each of those directories, you have subdirectories or you have documents of various types. So each of these things can only live in one place. If you have a picture, it's within C users, Tamara Marnell pictures, and then there's that file. But if you want it to live in different places, you'd have to create a shortcut. You'd have to make a whole copy of it. And you can see how this is quite limiting with the amount of data that we need to store in modern society. So in the 1970s, IBM developed the relational database model, which you might see referred to as RDM. And this is what is popularly taught in library school classes and professional workshops today. So you will see structured query language, SQL, many workshops, many resources on that. In the relational database model, data is stored in tables with predefined columns and allowed formats. You say this can allow long text strings or integers only, or dates with this particular format, or a set. It can only contain one of these three values, and so on. And then individual records are in the rows of the tables. And then you can use SQL to manipulate, create, and retrieve this data. So the SQL statements can use the unique values in each of these rows to join tables together in complex combinations and extract whatever information you want out of it. And unlike the hierarchical model, where one object could only have one parent could have many children, but you were really restricted in where things lived. In SQL, you can have many to many relationships. So here's a diagram of the SQL database that we have behind Archives West, our regional finding aid aggregator. And so it has these various tables like all users of the system, all the repositories in the system. At any one time, we have typically around 40 repositories. There could be more or less in a given year, but usually we have around 40,000 finding aids in about 40 repositories. We have the ARCs table, and ARC, it's lowercase here, but it's an acronym, and it's Archival Resource Keys. This is the unique identifier that we use for all of our finding aids. It's a standardized identifier. It's not Orbis Cascade Alliance specific. And then we have other tables to support the website. So you can see these solid black lines represent relationships between these tables and how you can use values in one table to look up values in another table. So every ARC, each of our unique finding aids has a repository ID. And every job that we run, these are the upload or harvesting jobs to get finding aids into the system. It will also have a repository ID. So this diagram does not actually contain a many-to-many relationship. I listed that as a strength of relational databases, but in reality, developers don't tend to use it, and instructors don't tend to encourage it, because a many-to-many relationship would typically mean you have to duplicate data between tables. So for example, if you had a database behind a website with blog posts, and each of those posts was in a posts table, and then you had tags that you want to associate with these posts so people can find them, and you have a tags table. If you were to just put the string of the tag associated with a post, what happens if you want to change that tag later? You then have to change it probably in multiple places because you've got unlisted the tags as strings in that post table or in a separate table that join the two together. So instead of replicating data, we tend to split many-to-many relationships into multiple one-to-many relationships. And you get the same result of having the flexibility of various records being related to as many other records as you want, but you're not forced to update something in multiple places because each table would only have one ID. An example in this Archives West database is this harvest table. This acts as a bridge table. It is not only a bridge table because it contains other resource information, like whether the resource was downloaded successfully from ArchivesSpace, whether it was uploaded successfully by the job. But the many-to-many relationship would be between this ARCs table and this jobs table. You can imagine a finding aid can be affected by many jobs. People could be updating that finding aid in ArchivesSpace and rerunning jobs. Also, jobs can affect many finding aids because we allow batch imports. So you do not see a direct link between ARCs and jobs. We're not putting the ARC listed as an array in the jobs table. We're not putting all the jobs ever run for an ARC within the ARCs table. We instead have this harvests processes table. So a job can generate many harvest processes, and an ARC can also be associated with many harvest processes. And each harvest entry only has one job ID and one ARC. So this way it's a one-to-many relationship between these, meaning each harvest only has one ARC, but an ARC can have many harvests. And the same deal here, this is one-to-many. And the end result is that you can bounce between these two to find what are all the jobs ever run on this particular ARC, or what are all the ARCs affected by this job, using this table as a bridge. So here's an example of how you can use SQL to look up information in one table based off of value in another table. This is a very simple example. So the repos for the repositories table has various information like the name, the URL, the various codes like MARC and OCLC associated with it. And then each ARC has one repository. So you can look up, for example, the name and URL of the repository that an ARC belongs to by joining these two tables together. This is how you do it in MySQL. select repos name, repos URL from repos, join arcs on repos ID equals arcs repo ID. So those are the two fields that have identical values in them to match on. And then we restrict this query to where the arc value in that arcs table is this. And it will say that this particular arc belongs to the Oregon Historical Society Research Library, and this is the URL of their website. Here's a slightly more complex example of getting data from tables that don't have a direct link between them. So if we go back to, we have this views table, which stores information from Google Analytics of how many times certain finding aids were accessed and the dates. I have a regular job to extract that information and put it in this table so we can query it quickly. And that only has an arc in it. That's what's in the URL that Google receives, is the arc at the end, and that tells you what finding aid it was. It has no information about what repository it was in. So if we want to grab all of the views of finding aids that belong to a particular repository or a range of repositories, if we know the exact repository ID, that's easy. That's just these two tables. But I have a more complex situation here where I want to get the views for all of the repositories belonging to the University of Washington because they have multiple. So in this case, I'm querying, we're doing the same kind of join that we did in that previous simple example, but then we're joining a second time. We're going from views to arcs to repositories, if you can imagine that chart again. And then we're saying where the repository name is like University of Washington, because all of those repositories start with University of Washington, restricting the date views between October 1st and October 31st, 2024. And then because what I'm fetching here is the name, count of the distinct arcs that were viewed in that month, and a sum, I have to tell this query what to sum by, because otherwise it's like, what exactly do you want me to add up? So we say group by repositories name, and this is the example output where you would get that the UW Ethnomusicology Archives had 1,062 arcs, and those were viewed 1,723 total times in October, and then those two other repositories. So I am not intending to teach you how to do SQL in this presentation. As I said at the beginning, there are many better tutorials out there to teach you how to do these things. And one of them is from the Library Carpentries, which is completely open source and free, self-paced. There's a link to it on the course website for you to go, and you can install a very simple database on your own local machine and start playing with it. So that shows you the power of SQL and relational database model, but not all data really belongs in a relational database model. It seems really amazing when you first learn about it, but you can't really stuff all kinds of information into tables of columns and rows. So if you think about the typical library record that we're working with, like a MARC bibliographic record, it has 999 possible fields, and they're not used in every record. They're probably very rarely used, a lot of them. So it would be quite silly to build an SQL database with one table with 999 columns just to fill those out. It wouldn't benefit at all from this joining structure and these advantages that these queries give us. So we need a different type of database for that kind of data. Same with those EAD finding aids that Archives West relies on, and all other kinds of descriptive documents. So for those, we have non-relational database types. And these became more popular in the 21st century as data got bigger and bigger. We can also call them NoSQL databases. to differentiate them. And these databases simply associate a key with an object or a value. This object can be anything. So there are many types of non-relational databases. The two I'm going to highlight are the two that we will most likely actually encounter during our work as systems librarians. And the first is key value stores. So this has a so-called quote unquote opaque value. It's a key, probably like numerical or alphanumerical, and then it has some value that the system doesn't know or care what it is. It's just a blob. It could be JSON, XML, a video file, an image file. It could be a mix of various things. It doesn't know or care. All it knows is that this key is associated with this thing. Here you go. So that allows for very fast writing and reading processes, but it means you don't know anything about the objects that you're fetching until you actually get it back. So document databases are like enhanced key value stores where the data is quote unquote transparent. The system actually knows what the structure is, what it's supposed to contain, so that it can query it in some way. So this makes this ideal for those library applications where we are trying to ingest tons and tons of descriptive data like MARC records or EAD records and make them searchable. Here are some popular document database programs that you might see, especially if you dive into the open source world. Apache Solr is everywhere. That is the document database that is used by the open source discovery projects Blacklight and Aspen, and also ArchiveSpace if you work in the special collections world. And this document database, you define a schema to tell it what is in these documents that you want to harvest. It will then, when you harvest a record, for example, from your ILS, it will look for those fields and it will index them. And in the next section, we'll get into what indexes are. BaseX is the XML-specific document database that we use for Archives West. So while I showed you an SQL diagram earlier on, that was a small subset of the data that is actually used for Archives West. It's what we're using to run the website, basically. But the contents of the finding aids are all in BaseX, because that makes more sense than trying to build a table and open up every new EAD and put a gazillion different columns in there. So BaseX is what we use to index the finding aids and make them full text searchable. And I'll get to that in an example in a little bit. And users, unlike Solr, where you tell it exactly what the scheme is of these documents, BaseX will just ingest XML that can be anything, and then users can use the functional programming language xquery to extract whatever information they want from those documents. MongoDB is another popular program that you might see in various applications that people share, and this is specifically for creating databases of JSON. And there's a free community version, and there are also paid enterprise versions of MongoDB. I don't have specific examples, but I have encountered it in various projects, so I'm mentioning it here. So indexes. What are indexes? We use the word indexes a lot in library science, but I don't think anybody ever actually explains to me what an index was until I had my own light bulb moment while making Archives West a couple of years ago. So we say that the search bots are crawling websites to add to Google's index, or we say we can't use Alma right now because Exlibris is running their annual re-indexing job. And we just accept indexes are a thing that are important. It sounds really fancy and technical, but like a lot of the other terms that we have explained during this series so far, like client and server and password, it just came from English. It's not a actually fancy concept. Way long before computers, 17th century is what I saw some sources say. Textbooks and reference materials contained back of the book indexes, or sometimes they might be indexes that are standalone, like for a very large collection of reference materials. But they're simply alphabetical lists of subject headings with associated page numbers. For a standalone, it might be an associated book volume. And that's really all it is a list of extracted information that is important, and then a pointer for where to find it. So a database index would be something that an application can use to quickly deliver whatever information you need to request frequently, instead of combing through large amounts of data. So here's an example from the acquisitions text by our shared content program manager, Jesse Holden, originally published 2017, also openly licensed and available online. So this is the index that is at the back of his text in the appendices. The first three entries in the A's are academic libraries, access, and acquisitions with the subheadings. So in order to use this, if you just want to read whatever he has to say about acquisitions and archives specifically, you just turn to the back of the book and say, that's page 103 to 106. Awesome. You turn to page 103 to 106 and can read exactly what you need. You don't have to scan through 102 pages before you get there. So that makes your fetching job as a human a lot faster. And computers do exactly the same thing. So here's examples from Archive West. As I mentioned, we have over 40,000 EAD finding aids at any one time. Some of these are hundreds or literally thousands of pages long if you print them out. I have received requests for some of these large finding aids because printing them was just impossible, because it was literally over 2,000 pages. That is a ton of information for a system to have to comb through every time somebody wants to keyword search it or extract other kinds of information from it. So even though BaseX is a very efficient program and I can put it on the most powerful machine available through AWS, it takes an excruciating amount of time to comb through that many documents in whole. And not only if you're doing a full text search, but also to create a list of facets on the side so that people can further refine their queries, and also to extract the abstract so they know exactly what they're looking at before they click on it. It took, when I was experimenting, at least 40 seconds to do these things. And nobody in 2024 has that kind of patience for a query. So instead, our application uses BaseX to build indexes. So there's a full text index that stores tokenized words or phrases with pointers to the documents and exactly the node that they appear in that document. So when somebody types in a word, it looks up that word in this index, and then these are all the finding aids that contain it. Similarly, there's a brief result index that contains only the titles, abstracts, and upload dates, because that's all we need to present in the interface. So when that full text index comes back with 200 records, we don't have to open up 200 original finding aids to get that information. We just go straight to this brief result index and say, give me these entries. And then we have multiple facet indexes, which we build custom based off of the control axis, nodes for subjects, persons, geographical locations, and so on, and then the arcs of the documents that contain them. And I have an illustration here of a subject facet index for one repository. So this is simply a new document. When somebody uploads a finding aid to Archives West through the management interface, a script goes through and it fetches these control access subject headings and puts them in this document. For example, if that finding aid contains advertising and marketing, slot the ARC here, or agriculture, put it here. So we have 40. Let's assume we have exactly 40 repositories, which we don't, but pretend we do. We have 40 documents that are these nice condensed references that a script can use to look up. So if somebody is using the browse feature and they click on artifacts, it will just open these 40 short documents and look for the term with the text artifacts. And these are all the finding aids that are associated with it. There you go. Or vice versa. If somebody does a full text search and this finding aid that has the ARC ending 76818 happens to come up within that set of results, we can just open these 40 documents, look for all of the instances of this finding aid or any of the other finding aids in this result set, and return the associated subjects. So again, you don't have to comb through 200 original documents and extract their subject headings, because we have this very nice short index. And that's how you can use Archives West without going insane, is because of these indexes. So Archives West is not unique. I did not come up with something amazingly original. Nearly every discovery index you work with, or discovery interface you work with, is going to rely on indexes to similarly not drive their users insane. And in Library World, we are working with crazy amounts of descriptive data. So especially if you are working with your discovery layer and you have millions of bibliographic records in that discovery layer, of course, it's going to run on indexes. It's not going to run on those original records in MARC or Dublin Core or BibFrame or whatever you're using. And so even if you're not building a unique interface or working with one like Archives West, you are certainly going to run into issues as a systems librarian where the trouble lies in the indexes. The index is not getting updated usually. So here are some real world situations that have definitely come up within the Alliance and will probably almost certainly come up for you at some point. Are catalogers creating new bibliographic records, and then they go to the public-facing catalog and they test search and it's not coming up. This is probably because the job that indexes that new record has not run yet, or it has failed. If it was supposed to be up in 15 minutes and it's not, it was supposed to be up overnight and it's not, problem is in the index. Another common situation is your library changes the name of a location, but the old name is still appearing in those facets. And you've got your colleagues asking why. It's probably because that facet is a separate index, and you are going to have to re-index every single record that is in that location so that the system updates that section, your interface. And a final example is your colleagues expect known records with a certain local field to come up. They've decided they've got this collection. They're going to mark it all the same way using this unique local field. And they try to find it in the catalog and they can't. And that could be because your catalog is probably running searches on an index of certain fields. And if you're using a unique local field, it's not included. So it's just not going to make it over to the interface. Even if you can see it there in your ILS, it doesn't exist on the catalog side, and there might be some work you need to do in order to add it to that index. So that was my brief overview of databases and indexes, and I do encourage you to do further learning using those library carpentry courses or the many other resources that are out there to get started.